Good morning, good afternoon, good evening, everyone. Welcome to the Earth Data webinar. It is our pleasure to have Professor Teresa Ubide speaking with us. Teresa grew up and received her education in Spain, and before she moved to Dublin, Ireland for her further research, and then moved to Australia almost 10 years ago, it's 9 years ago. So she has done a lot of interesting research on volcanology as well as the igneous petrology. She uses a lot of high-resolution geochemical methods to define the process, as she's going to tell part of her research on the deep magmas that are generated from the Morgel OIB today. So with that, Teresa, I'll give the rest time to you. And the webinar is relatively flexible. So normally we ask speakers for 40 minutes to talk, but you make it shorter or slightly longer, it should be all right. So this talk is recorded, but we don't know whether it will be still be preserved like 1 hour from now. But let's see how it goes. If it's good, then it will be posted. If not, then it will be deleted and people will forget it forever. It's only in the memory of the participants in this room. So with that, Teresa.
Many thanks for having me, and I'm very excited. I'll share my screen. Can you see my screen, my presentation? Yep, okay, cool. Okay, so I'm super excited to talk to you about deep magma histories in mid-ocean ridge basalts, as well as ocean island basalts, and how we can investigate them with high-resolution petrological and geochemical methods. Before I start, I'd like to acknowledge that this is collaborative work with fabulous students, postdocs, and collaborators around the world who make the research really interesting and fun. So thank you, everyone. We care about volcanoes for many reasons, including that they are posing major natural hazards, they can affect air traffic, and they can even impact the climate for short term. On the other hand, they also are important because they build our oceans and they also build our continents, and they can sometimes even accumulate metals that are essential for our green energy transition. So, for example, one electric car requires more than 50 kilograms of copper, and wind turbines need almost 5 tons of copper each. So we need a lot more copper and other metals that are critical for the energy transition that we used to, and we need to be able to understand how they accumulate, including in magmatic systems. So I'm very interested in understanding magma storage and magma transfer through the upper mantle and the crust. And the more we study volcanoes and magmatic systems, the more we realize how complex they are inside, and how the volcano we see at the surface is only the tip of the iceberg. It's actually fed by a really complex mesh or network of conduits and reservoirs that are mostly crystal rich. So this is a new paradigm of magma plumbing systems where the majority of what we have is very crystal rich. More than 60% of crystals make a mush that is not eruptible. And then the pockets of magma can be quite transient. And these are the ones that are movable and can lead to eruptions. So we have this new paradigm of new plumbing system fed by mush with transient magma pockets. And we are very interested in understanding in this type of systems, what are the tipping mechanisms that make the system erupt versus not, grow the crust, grow the ocean, and potentially even accumulate metals that are essential for renewable technologies. But also, we are looking at this paradigm from several levels of magma storage through the crust, what's called the transcrustal magma plumbing system. And that's something that works really well for arcs, particularly continental arcs at the peak of the heat flux or at the peak of the arc magmatism. But I've become really interested in understanding how these mush systems and mush architecture look like in different tectonic settings. So not necessarily in continental arcs, but also in oceanic arcs or mid-ocean ridges or ocean island basalts. And I'll be talking about today about those last two, mid-ocean ridges and OIBs. Starting with MORBs, mid-ocean ridge basalts grow our oceanic crust. And they are basically our largest volcano factory on Earth. They are very unassuming, mostly occurring under the water level, so they are not very um, they are not easy to spot, but they are actually producing the largest amounts of magma on Earth. Because the Earth is like baseball that has all these seams going around the ball. The mid-ocean ridge system is the same, and it moves, it pushes plate tectonics and generates ocean crust. What we get in mid-ocean ridges is mostly basalt. So the magmas in morb settings in mid-ocean ridges are very mafic, as opposed to, for example, what you get in a continental arc, because they don't have space or time to differentiate. So you get basalts, pillow basalts in contact with the water, and below that you would get gabbros, so the plutonic equivalent. But they are very mafic rocks and they are not evolved. So you would think that maybe they have relatively simple plumbing systems. However, there's a lot of complexity in them. If you look at the geochemistry of global mid-ocean ridge basalts, which are represented here by gray dots in a calcium to aluminum ratio versus magnesium oxide plot, you can see that to reproduce the wide scatter of gray dots of global morbs, if we start crystallizing an initial composition of a parental morb liquid, which you can see on the right-hand side, to be able to reproduce all the scatter of gray dots, we need to think of crystallization at a wide range of pressures up to 10 kilobars. Otherwise, we cannot reproduce the low concentrations in calcium relative to aluminium in the samples that are around where the black star is, which is the median Southeast Indian ridge morb. So this is interesting because what happens at high depth on those high pressure models is that clinopyroxene becomes more stable. The stability field of clinopyroxene increases with depth. And so you start to form clinopyroxene quite early in the evolution here. And then you manage to drive the leftover liquid down in this way. But the problem is that if this is the case, then why do we not find these clinopyroxenes very commonly in the erupted morbs? Erupted morbs have little pyroxene, and also in the gabbros that are exposed in sections of the ocean crust, of the lower crust, we don't have much early pyroxene petrographically speaking. It looks like it's a late intercumulus phase. So these inferences build what was known as the pyroxene paradox, where the morb geochemistry suggests that you have deep fractionation of pyroxene, so fractionation at depth, whereas there's no pyroxene in the rocks. So where is deep early pyroxene that we don't see in the rocks? So this is a very interesting observation. And the other interesting observation is that morbs are actually enriched in incompatible elements compared to what you would expect from normal fractional crystallization. And this has led to the understanding that there's a lot of reactive porous flow in these mid-ocean ridge mush systems, where infiltrating magmas react with the mush, dissolve some of the mush, become enriched in incompatible, remain enriched in incompatible elements, but become enriched in other elements as well. And that can also account for the geochemistry of morphs. So there's a lot of discussion about the origins of morphs, and there's wide acknowledgement that there's reactive porous flow, there's recharge of magmas, there could be deep fractionation of magmas, but it's hard to resolve all of these processes. So from a petrological perspective, what we thought is that, if you have these very complex crystal mashes, you should be able to see some of those complex records in the actual crystals. But of course, because these crystal mashes are preserved as gabbro, so plutonic rocks, many of the zoning patterns become erased via diffusive reequilibration. So how can we get to read protracted magma histories in plutonic rocks? And that's where we turn to slowly diffusing trace elements in pyroxene. So we had done previous work in pyroxenes from volcanic settings, in which we had observed that slowly diffusing cations that are trace elements like chromium or rare earth elements or high field strength elements like zirconium, actually preserve very protracted magma histories because they are very slowly diffusing, and therefore they're able to hold on to those magmatic processes they have seen at depth. So this is an example of study at Mount Etna in Sicily, where we collected samples across recent activity, and we found that we could track the arrival of new magma into the mush feeding Mount Etna as enrichments in chromium in the final rims of the crystals, as you can see here, suggesting that these new chromium-rich zones are forming from mafic magma, entering the system and triggering eruptions. So from these inferences from the volcanic environment, we thought, let's try to see if these slow diffusers, such as chromium, can keep the record in the plutonic system as well. So what we did is we used the pyroxene approach on gabbros from Atlantis Bank, which is a core complex that exposes some of the lower oceanic crust. And we particularly focused on a section of hole 735b from an ODP exhibition that expedition, that had been shown to be particularly primitive and a good recorder of mafic replenishment into the mush. So we wanted to test if we could get samples from this section and see if the pyroxenes were able to reflect any of the earlier or deeper history. We were happy to see that the rocks looked really good. They are very fresh, and they are formed mostly by plagioclase, which is the main cumulus phase, which you can see in white here in this plain polarized image under the microscope of the thin section. There's also some cumulus olivine, and there's also clinopyroxene, but the clinopyroxene is intercumulus, as you can see in this example here on the right. It's kind of filling in the gaps texturally. So it looks like it's a late phase. So it doesn't look like an early phase at all, but we said, okay, let's have a look at what happens if we map those intercumulus looking clinopyroxenes for trace elements. So I'm going to look at that one initially as an example, and this is zirconium. So you can see that the main feature of this pyroxene is that the rim of the pyroxene, the outermost part, is massively enriched in zirconium, which is an incompatible element. And this very strong enrichment agrees with reactive porous flow through the crystal mush as a late process, controlling the crystallization of those final zones. Not only it is enriched in zirconium, but also in other high field strengths like titanium, as you can see here. But what we could also start seeing is that there seemed to be an earlier history of processes recorded in the inner portions of the crystals. And if we look at chromium, which based on observations is the slowest diffuser of the elements that clinopyroxene incorporates, it turned out that it had a beautiful history of successive enrichments and depletions in chromium up until the end of the crystal, where you get the depletion in chromium that correlates with the enrichment in incompatible elements, reflecting reactive porous flow. But it was very interesting to see that the core of the crystal, which was very rich in chromium, very primitive, presumably formed from a very primitive magma, it looked like a fragment of a crystal, a broken crystal that may have been transported from depth. So we got really excited because maybe these fragments of crystals were the missing piece of evidence of early deep fractionation of pyroxene in mid-ocean ridges. But then it was incorporated into an ascending magma that eventually emplaced at a shallow level and formed the rims, which are indeed in the cumulus and late, but not the entire pyroxene is late and intercumulus. It has an earlier resorbed or transported core. Of course, this is only one crystal, so we wanted to see if this is something that we can see across the entire thin section and across other samples from this section of the slow-spreading Southwest Indian Ridge. And so what we did is, in addition to these laser ablation ICP-MS maps, which gave us very nice quantitative information for a range of trace elements, we also did entire thin section maps of certain trace elements at the Australian synchrotron using the XFM beamline. So this allows you to map a selection of elements, but a very high spatial resolution and for the entire thin section. And then you can start to see that those features that we saw on that initial pyroxene were also reflected in other pyroxene. We were really excited about this. It was not an oddity, it was quite a common process. And so what we did to try to find those early cores is that we did a combination of elemental maps obtained by synchrotron XFM together with petrographic image uh, microscope images. And so we applied some machine learning analysis to try to find where were the cores, those resorbed cores in the pyroxene. So the machine learning algorithm found the CPX cores in our pyroxene crystals. And this is a phase map that shows those cores as dark green colors. You can also see the pyroxene mantles, which are the majority of the pyroxene in this thin section, which, if you remember before, recorded those injections of primitive magma as oscillatory zones. And we also see pyroxene rims in green, which are enriched in incompatible elements, in addition to lots of plagioclase, which you can see as gray colors, and olivine and other phases. So this was really powerful because it was able to quantify the amount of core material in the pyroxenes of a given thin section. And it was not very much. Around 4% of the pyroxenes were cores, which agrees with the fact that these were rare, resorbed, transported crystals, potentially coming from deeper in the plumbing system beneath mid-ocean ridges. Not only we could look at the cores, we also could look at the rims. As you can see here, we see the massive enrichment in zirconium at the rim, and not only zirconium, also other incompatible elements like the rare earths. But you can see clearly the effect of diffusion, which is particularly enhanced in the plutonic environment. As you move from zirconium to cerium to ytterbium, where we increase diffusion rates, and the zoning patterns become progressively more diffused and raised. So you can see the diffusion impact is very large in the plutonic environment, but we can use the slow diffusing cations like zirconium or chromium to define specific zones in the pyroxenes and extract data from them. So these are data extractions that we can then put together and use to build traditional elemental plots, bivariate plots, or rare earth element plots, for example, normalized to chondrite. So all of these lines that you can see here are extracted clinopyroxene compositions from cores in blue and rims in red. And you can see that they are reflecting different enrichment in rare earth elements, higher in the rims, which are affected by that process of reactive porous flow, than in the cores. And in the rims, we have negative European anomalies, which we don't observe or very minimally in the cores. This suggests that the rims are indeed late and form after the generation of the plagioclase mush, whereas the cores are formed before the plagioclase mush is developed. So this supports the notion that the cores are deeper and formed at depth where plagioclase stability is lower. We can calculate the equilibrium melts with the clinopyroxene cores and the rims, which reproduce those patterns we saw in the clinopyroxene. But the benefit of this approach is that we can now compare these liquids with erupted morphs in the region. And we can see how the cores have those flat rare earth element patterns with very minimal European anomalies, which agree with erupted cores. And this is very interesting because it brings a link between the erupted morphs at the top of the system and the deep pyroxenes that are forming from primitive magmas early in the history of the mid-ocean ridge melt, presumably at high depth because they don't have negative European anomalies, meaning that they formed before substantial plagioclase removal. So this was really exciting because we could connect the volcanic record with the early magma differentiation, and because we could potentially link the cores of the pyroxenes to deeper histories in the more plumbing system, whereas the rims are related to shallower processes of reaction. If we go back to thermodynamic modeling and phase diagrams, this is reflecting pressure increasing down and temperature increasing to the right from a parental morb composition. You can see the liquidus line is on the right-hand side in white. And from right to left, you start to crystallize as you drop the temperature. And so you can see that the stability field of clinopyroxene expands massively as you increase depth. And so it is reasonable to think that if you start fractionation of morb liquids at depth, you would generate quite a lot of pyroxene, and then you could move those liquids up. The pyroxene would become unstable and largely resorbed, but you may be able to find some of those early cores in shallower portions of the system if they were able to survive. As I showed you earlier, we see up to 4% of early cores surviving in the plutonic environment. So not many at all, but we were lucky to find some and make that shallow to deep connection. Actually, from these thermodynamic models, we can extract liquids at any time, and we can extract liquids from this point in the evolution, and then, which is this one here. So we start with the parental morb liquid, we fraction it until the star, which is the extract at 8 kilobar and 1235 degrees C. And we can then move that up with, modeling polybaric evolution to shallower levels in the crust from 4 kilobars to 0.1 kilobars and continue fractionation. And with this type of process of polybaric fractionation, we can easily explain the range of morb compositions erupted in morbs globally in terms of calcium, aluminium, and magnesium space. So that was really exciting to be able to connect the petrographic observations, beautifully eased by mapping slowly diffusing trace elements which reflect those early cores with the geochemistry of erupted morbs. And so with all of these, what we could do is build an updated view of how the plumbing system of mid-ocean ridge systems may look like with this polybaric concept of deep fractionation at upper mantle depths, forming pyroxenes because they are favored at high pressure, and then extraction of those liquids to shallower levels in the crust where you get extensive evolution, including formation of lots of plagioclase, which forms the plagioclase mush, which locks some of those early rare resorbed clinopyroxene relics in, and further crystallizes the pyroxene mantles, and finally the pyroxene rims, which are reflecting those processes of reactive porous flow through the crystal mush. And the reason why you have them massively resorbed and very rare, these cores, is because of the impact of the decrease of the stability field of clinopyroxene as you decrease depth. So this is all published recently in EPSL, and I would like you to have a look if you are interested, and happy to take on any questions on that. But I would like to now jump to other basaltic systems in the oceanic setting, which are not linked to mid-ocean ridges, but rather to ocean island basalt systems, such as, for example, the Canary Islands. So these are interesting, very different compositions. In the particular case of the Canary Islands, very alkaline. So very different geochemical affinities and formation. They are considered messengers from the deep mantle, which melts at high pressure and low degrees of partial melting to generate these alkaline magmas that are silica unsaturated. But we're gonna look at these basalts from a very petrological perspective. So we're gonna look at samples from El Hierro that you can see on the left there, as well as La Palma, which are the youngest islands of the Canary archipelago and host the most recent eruptions. So now we've been looking at mostly plutonic rocks, and now we're moving into the volcanic environment. And this is how basaltic rocks often look like. So they have lots of crystals that have been recycled from the mush, and they have complex zoning patterns, as you can see in this XFM map from the Australian synchrotron. In here, the colors reflect composition. So red is calcium, blue is iron, and green is chromium. And so those reds, those big crystals that you can see here are basically pyroxenes with strong zoning patterns and very clear chromium zonations, as we saw also in the plutonic environment. Okay, so if we want to look at magma composition and we make a bulk analysis of this rock, what we're going to get is a mixture of the liquid, the magmatic liquid that is represented by the ground mass, as well as all the crystals from the mash that this liquid has incorporated on the way up to the surface. And so we noticed that the impact of these crystals on the geochemistry of the bulk rocks obtained was very large. So in El Hierro Island, there are outstanding exposures of feeder dikes and associated lava flows that have similar, or in some cases, contrasting textures. So within this same system, the lava is crystal poor, apheric, whereas the dike is porphyritic and has lots of mafic crystals. And if you look at the compositions from these 2 points of the same system, you can see that the magnesium content in the porphyritic feeder dike with lots of olivine and pyroxene has almost twice as much MgO content as the lava from the same system. So basically, those magnesium-rich rocks are dominated by cumulates. They are not actually reflecting very magnesium-rich compositions in the feeder system. So actually, we looked at published data from El Hierro and our new data as well, separating them into porphyritic rocks, lots of crystals, very high magnesium, apheric rocks without crystals, melt inclusions, obviously melt records, and these are just simply unknown texture of the published literature. And what we could see is that the crystal-free samples we had a very clear distribution peak at around 5 weight% MgO. So that was very interesting because in OIB systems, they are considered traditionally like messengers from the deep mantle. And often the compositions used as parental liquids are the very magnesium-rich compositions. But we found these are mostly cumulates in El Hierro and other Canary Islands and other OIB systems worldwide. And so this was interesting because actually these mafic magmas are not that mafic after all, if you look at the pure liquid compositions or true liquids. And this peak in distribution in many OIBs globally may reflect an eruptible sweet spot of chemical and physical parameters that may lead to this magma erupting at the surface. So what we then did is assess the filtering of these magmas through the plumbing system of OIBs. And so through thermodynamic modeling, what we found is that if we start with a parental magma composition and we fractionate about 50% of crystals, which is what this represents, we reach that sweet spot of 5 weight% MgO at a point where the density has decreased, the viscosity has not yet increased, but the water content has increased, so that if we are at the right depth and we have not only water but also CO2, we may reach volatile saturation. And of course, this is important in OIB systems because they are typically CO2 rich. And so what we found is that maybe these MgO 5 weight% liquids become most eruptible, or they get this eruptible sweet spot and they become propelled to the surface when they reach volatile saturation below the moho depth and erupt preferentially over other compositions, with the implication that then OIB edifices may be built by magmas that are less extremely mafic than previously considered. So as we were finalizing this paper, the nearby island of La Palma erupted at the end of 2021. And it was a very dramatic eruption that thankfully didn't lead to any loss of human lives because everyone was evacuated. But it had a very large social impact because thousands of people were evacuated and could never go back to their homes because their entire villages were covered by the lava from this eruption. So the eruption lasted for 3 months. And so what we did is we collected samples with collaborators in Spain across the entire 3 months of eruption. And we wanted to see if there was variation in the magmatic liquid erupted. And so to do that, because we knew of the impact of the crystals on the bulk rock composition, what we did is to analyze only those liquid compositions which are represented by the matrix or the ground mass of these lavas. So this is an image of one of those lavas in reflected light at a laser instrument. And so you can see what we do is we do rasters across the microcrystalline matrix that then we send to the quadrupole mass spectrometer for major and trace elements, or to the multi-collector mass spectrometer for strontium isotope ratios. Everything is done in situ really rapidly in a matter of minutes, and we do it many times for a given thin section. And so with this, we can get a true signature of the geochemistry of the magmatic liquids without getting modified by the crystal cargo picked up on the way. So the idea is that we can assess if there are subtle variations in the magma chemistry as in this case, the eruption progressed. And this was published in Science Advances, and in the supplement there is all the technical details of the method if you want to apply it in your labs, and I'm also very happy to help and be in touch. So we have samples. This is the lava flow from the lava field from the eruption. This is the main cone here, and it got to the sea. It built the island of La Palma while also covering many houses and villages and infrastructure. We were able to collect samples across the 3 months of activity and then assess the chemical variations in ground mass, which you can see here in the green big dots through time for MgO, which if we compare to the whole rocks, which are up here, are a lot lower, and cluster around that eruptible sweet spot that we had just defined in El Hierro and other OIBs globally of around 5% MgO. So again, we are seeing that eruptible sweet spot erupted again in La Palma very clearly through the 3 months of eruption. Whereas in the whole rock, you see magnesium contents are strongly modified by the accumulation of olivine and clinopyroxene as the eruption progressed. So if we look at the matrix, we don't see many variations in magnesium content, but we see variations in strontium isotopes. Through the eruption, we went from highly radiogenic to a mixing trend and then 2 N-member strontium isotope compositions. And these type of variations correlated with eruptive activity. The lavas of the eruption were blocky, thin, and voluminous at the beginning, and more rapid, fluid, and channeled into tube towards the end. The impacts and hazards of these two styles of volcanism are different, and so it's very useful to see variations in the chemistry that reflect in volcanic activity and hazard potential. We could also identify that there were events of recharge potentially at the beginning, after this eruption break, and more or less in the middle of the eruption, where we have the split in isotopic compositions. And not only we saw differences in isotopic ratios, we also saw variations, for example, in incompatible elements, which decreased progressively as new basanitic mafic magma replaced the resident mush. And then interestingly, we saw a tipping point about 2 weeks before the eruption ended, where the incompatible elements in the matrix started to increase, suggesting fractionation of the liquid, which presumably happened because the fueling magma of the eruption stopped. So this was interesting to see that we could track the end of the magmatic fuel of the eruption and kind of forecast the end of the eruption together with other evidence from geophysical monitoring and gas monitoring, which was really interesting. The other benefit of this matrix approach is that we can couple it with clinopyroxene to calculate pressures and temperatures of magma storage. So throughout the eruption, our clinopyroxene matrix barometry indicated upper mantle storage, so again below moho level. And this was also corroborated by high precision fluid inclusion data throughout the eruption. And also in agreement with the deeper cluster of seismicity that was detected throughout the eruption. There was also a shallower level of seismicity that could represent some transient shallow crustal storage, but the majority of magma storage in this case is happening in the upper mantle. And another thing that we saw is that we could link all of these observations to data from earthquakes, tremor, and SO2 mass SO2 flux, and see that many of the recharge events we had identified geochemically were also reflected in other monitoring sites, such as earthquake, magnitude, tremor, and SO2. Further supporting the idea that we can identify individual batches of magma feeding the system that we had particularly well identified with the strontium isotope data, all in situ with the matrix throughout the eruption. So this was exciting result. These were exciting results that again supported the notion that in these OIB systems of relatively low to mid magma flux, magma storage is happening predominantly in the upper mantle. And not only we get basanites and tephrites, which is the majority of the magma erupted, but recently one of my postdocs, Eugene Jegal, published a paper on plagioclase, recycled anticrysts from phonolite mashes also stored in the upper mantle. So we have predominantly upper mantle storage and only transient crustal storage feeding to eruption in OIBs of low to mid magma flux. This is different to say Hawaii, for example, which has high magma flux and where storage of magma is really quite shallow. And that's possible because of the increased flux on those hotspot settings. So, but what all of this is telling us is that we have a quite complicated view on plumbing system dynamics and architecture, depending on which tectonic setting we are at. So we started the talk with this kind of transcrustal or many multi-level magma storage through the crust, which we see, for example, in arc volcanoes. But if we find mid-ocean ridges, we start to have not only shallow storage, but also upper mantle storage. And this also happens in ocean basalts that have low to mid magma flux, whereas these are the OIB systems of high magma flux, such as Hawaii. So plumbing system architecture can be quite complex and quite different depending on tectonic setting, which then controls magma composition and volatile budgets, volatile saturation, and therefore the architecture and dynamics of plumbing systems. So we drew this kind of more tectonic system scenarios of MASH systems in this recent Encyclopedia of Volcanoes chapter on petrological characterization of magma storage, which you can access freely and will be eventually published when the third edition is out. But even this, which tries to convey the complexity of plumbing system architecture, is still a simplification of reality, no? We've seen that, yes, in mid-ocean ridges, we have upper mantle storage. We've seen that the same happens in OIBs, but only in the low flux ones, not in the high flux ones. And that's all hotspot systems in the ocean. But one of my former PhD students, Tamini Tapu, published this nice paper of the hotspot track in Eastern Australia, which is the largest continental hotspot track on Earth. And he found that, in the continental setting, magma storage is more complicated and is also controlled by plume flux. So I invite you to have a look at this paper if you're interested. And, if you go all the way to the arc volcanoes where we started, even if they are not the focus of this talk, they're also interesting because depending on if you are in a continental arc or an oceanic arc, the plumbing system architecture will be different. Maybe you are in an anomalous arc setting where also magma composition is different, leading to different architecture, and also magma flux. So you may have multi-level magma storage, as you can see on the left here in this sketch, when the magmatism is at the peak of heat flux, but it may be more patchy in periods of steady state arc magmatism. So all of this is actually really interesting, and I'm interested. I wanted to finish by saying that I find arc volcanoes growingly interesting, and we've done field work and already are working a lot in continental arcs like the Central Andes, as well as in more thin crust settings like Indonesia, super active and also linked to recent porphyry copper deposits. And, we bring all the samples to UQ in Eastern Australia, and we have these beautiful techniques, high resolution geochemistry to interrogate the rocks and, basically extract information from all the pieces of the puzzle. analyze the crystals and get all the information, analyze the liquids that are carrying those crystals to the surface, and basically deconstruct the mush and reconstruct the plumbing system architecture across tectonic settings, better understand how they are built, how they are triggered to erupt, how they are triggered to build the crust, and maybe accumulate metals that are critical for our green energy transition. Thank you very much.
Okay, thank you very much, Teresa. Now it's time for questions from our participants. So feel free to open your mic or leave a question in the chat and I can read the question on your behalf. How about so any questions from the participants? Or I can begin with the first question. So would you move to your, like I said, conclusion page? I think that's pretty much on the volcanism, Morb
Yes,
source, and the OIB. I think that's the I thought that
these
would
are.
be the last slide. Yeah, but it's good enough. Uh, so may I know that from your perspective, which one does this might be an analog for the lunar basalt source?
Ah,
How do we
so
modify the lunar basalt source uh, according to our understanding of the Earth scenario?
yeah, that's another one you could draw. Different again. So another
Mhm.
thing that this sketch has is magma composition. So in the arc volcanoes, particularly in settings with thick crust, you get to very mafic, from very mafic to very felsic compositions in shallow portions of the crust. Whereas in settings like mid-ocean ridges, OIBs, you have rare felsic magmas. You have some, but it's not so common. And I guess the same would apply to places like the moon, as you were saying, no? And so you could, and but then you have other constraints, like you have different architecture and everything. So I guess you could draw a different drawing for extraterrestrial plumbing systems as well.
Okay, questions? More questions? Yeah, feel free to open your mic.
Thank you.
Yeah, thank you.
Stop sharing to see if there's any chat.
Yeah, Joe. Okay, I have a question in the chat. Maybe can you read? And I can also read aloud. Uh, it also was really talks. Many thanks for your knowledge and thanks to the team who organized it. Okay, so it's a comment. Okay, that's okay.
Thank you.
I think we have. So, Zhao, do you have a question? I see that you open your mic.
Yes, thanks. And I have a small question about the formation of the OIB and based on the how to say it. There are based on the model of the OIB, there are several reservoirs in the crust and the mantle. So my question is about the depth of the about the depth of the reservoirs. Uh, is there any geochemical uh, how to say? Is there any geochemical proxy to identify the depths of the reservoirs?
Yes, thank you so much. So this is the OIB. We considered actually having two drawings because you would have just this part for high magma flux and just this part for low magma flux with very limited crustal storage. But in the interest of simplicity, we put them together. And this is basic. This top part is based in places like Hawaii, for example, which has very shallow reservoirs. Like there's two and very shallow in the top 5 kilometers of the crust. Whereas, for example, this bottom one, which is based on the Canary Islands or Cape Verde, are based are storing below Moho, which in those settings is around 15 kilometers. So, of course, depends on your regional setting how deep that Moho is. But the way you locate these reservoirs and their depth is by using geothermal barometers. So for example, using fluid inclusion barometry or mineral melt barometry that you apply to your samples and you locate storage. And then, of course, you compare that to geophysical data from seismicity, from earthquakes, to see if they should match. And of course, taking into consideration that many of the barometry we have has reasonably large errors. So you do want to apply a number of different independent parameters to see if you can finalize or agree on a general depth. Yeah, but thanks for the question.
Okay, thanks. Very thanks. Thanks, million.
Okay, next question, please. Let me continue with this question. So, to my understanding, that is great that we have the primary climate piercing the cores that we found, but on the other hand, that even the deepest of those climate piercing that come from are at best near Moho depth. So for those claims or hypothesis that some of the geochemists think that the source comes from Earth's core boundary, then any of the minerals, even they originate from Earth's core boundary, that they have been decomposed in the outer mantle into upper mantle minerals, but they are still going to be remixed at the magma, like the reservoirs that you have been drawn here. So there is no way that we can really keep those crystals anymore.
It's very difficult. So when we found, hold on, I'll just give me a sec. I'll find the relevant slide here. Can you see my screen? I'm not sure.
Yeah, I can see the screen.
Oops.
Yeah, I can see. Yeah.
This way. Okay. So when we found these cores that we identified with the help of machine learning applied to stacks of XFM elemental maps and petrographic images, they were not that many. So 4% of pyroxene in this thin section is the cores, which are primitive and they have no negative European anomalies. And some sections had none. So where we found them, they were in thin sections that had these complex zoning patterns where you could see that there was a complex history recorded. Many of these oscillations reflect recharge of mafic magmas coming into the system. And some of those mafic recharges bring the early cores in with them. But most of the cores become resorbed because of the fact that the clinopyroxene stability decreases as you decrease pressure. And so what we drew here is that those early cores that are easy to form at depth, if you're lucky enough to collect some because they are dense, if you're lucky enough to collect some with the magma as it goes up, they will become resorbed when the stability fold of pyroxene decreases. And so you will find some thin sections where you have the evidence of recharge via those oscillations have a little bit of cores if you're lucky, up to 4%, which is not much. And many thin sections will have no evidence. So it was good, I think, that we aimed for a particularly good section that had been identified in previous studies to reflect magma recharge and primitive magma compositions coming into the system repeatedly. So this is why we requested core legacy samples from this particular section to investigate, because we thought we had the highest likelihood of finding these hidden cores using slowly diffusing cations, which we were happy to find. But as you said, it's very difficult to keep them because they dissolve and you will only find them with these slow diffusers, particularly chromium, which is excellent because it really survives. So actually, the diffusion of chromium has not been constrained experimentally in pyroxene, but based on the observation that the sharpest zoning is always chromium, both in plutonic rocks and volcanic rocks, as I showed here, we understand that it's the slowest diffuser, followed by high field strength elements like zirconium, and then the rare earths. In the rare earths, diffusion has been well established, and the heavy rare earth elements diffuse faster than the light rare earth elements, as you can see reflected in the maps really nicely.
So if they are concentrated in chromium, do you also expect them to be relatively high ferric iron content, particularly in this
So
system?
the chromium content is very high in the cores and very low in the rims. And it preserves the zonation the best, even better, So
So,
this
so
was zirconium here, and that's chromium.
yeah, yeah. I mean for the ferric iron, but this is also ferric iron in the core.
Ah, okay, good question. Good question. Hard to measure, as you know, ferric
I know.
iron. The best approach I've seen lately is using the probe, no?
Mhm,
That there's now ways of doing it with the probe is quite tricky. But if you have secondary standards that you have independently measured with Moss-Bauer or
mhm, mhm,
synchrotron,
mhm,
then you can try to give it a go. I haven't myself tried to
mhm,
estimate iron 3
mhm,
to iron 2 ratio
mhm.
uh, by measuring them. I do calculate them based on, stoichiometry and charge balance. Yeah.
Yeah, unfortunately, that's not working very well for planar pyroxene
It's
for the stoichiometry method in terms of the
it's very
calculating parameter.
difficult. Yeah.
Yeah, I know it's very difficult by Zines. I mean, there are people in China, for example, Honglo Jiang from China University of Sciences, Beijing, Jintang Wang, they have all using the Zines, for example, to measure the climate.
Exactly.
Yeah, it's very challenging, especially if you use the anisotropy uh,
Yes.
of climate periods, making it much harder to measure if you have iron compared with garnet or compared with spinel. But it's a very important one because especially in this system, you see all the olivines or pelagic clays, they are very iron free. So this is
Yes.
the that is likely if they are enriched in ferric iron, then it will be, if there are a lot of ferric iron in the system, they are going to be enriched in this phase. Alternatively, it will be a system with a very low redox, as let's say people have been measured from this abyssal purity tests have shown us. So it will be very valuable, I think, for this
Yes.
one, especially to tell us the source, because I think that if this is for since this is the first report of the relic CPX, I think this ferro
I
iron
agree with you.
really means quite a lot to the community. Mhm.
Yeah, it will, I agree with you. It will be very interesting to calculate the difference in ferric iron
Mhm.
across the cores and rims. Yeah.
So the core is about like say, what's the exact size? Is like say 100 microns for this really
Yeah,
high.
it
Mhm.
depends. So here we have them, that's a scale, that's 5 millimeters.
So that's
And
a
the cores are the
700.
dark green.
Okay.
Yep, the dark
Okay.
green areas. It depends, but yeah. So
Mhm.
then, as you can see, there's not many, and they typically rounded, and they can be placed anywhere in the sample, I guess, wherever they became locked by the plagioclase mash, because all of this gray stuff is the plagioclase, which basically forms at shallow depth and locks the mash and traps those early cores if you are lucky to have them.
Mhm. Okay. Uh,
Mhm.
Okay, I think one alternative to do it without the Zens is use the machine learning to predict ferric iron, which our group do have a publication in American Mineralogist a couple of years ago to train a
Okay, that's
ferric
cool.
iron correlation with the major elements in climate. But it should be used very carefully because it depends on the any members of CVX we have, whether they really fall into that range, and and that is also mainly based on it is all based on the natural climate piercing. So it also has a
Mhm.
equilibrium, disequilibrium problem, and whether it have been further modified. So that's another thing. That's another thing. But I think that for stoichiometry, a method to calculate ferric iron for the minerals, generally a lot of them are relatively okay. Spinel is great, but I don't think used to calculate CVX ferric iron that method is valid at all. Uh, Sorry, having
Yeah,
so many
lots
questions.
lots to do in that space, I think. Lots of lots of
Uh,
lots of research in that space.
okay, any more questions?
Hi, can I ask a question?
Yeah, sure, please, Henry.
Okay. Hi, Teresa. I'm Henry from Zhejiang University, and now I'm visiting at UC Berkeley with Penny, with her.
Ah,
And
nice.
yeah.
Say hello.
Hello.
Go ahead.
Hello. I'm in the US. I have a question. That I'm studying the magnetic pluming system of oceanic large igneous province. And my
Uh-huh.
question is, which model do you think is more suitable for the oceanic large igneous province? Because you propose three models like ARC, OIB, and MO. So which model do you think is more suitable for the large igneous province?
I guess based on flux, it should be the high flux one, no? But then what does the thermobarometer say? That then you can tell me. What kind of storage depths are you calculating based on your rocks?
I think from is variable because from fluid inclusions we have get very deep depths.
Yep.
Use ramen in Penny's lab.
Yes.
Yeah, but based on the high flux, we think there maybe is a shallow
Shallow as
reservoir.
well.
Yeah, but using ramen, we have get a deep reservoir.
Okay, that's
Yeah,
interesting.
yeah. So what do you think is the suitable?
And yeah, I mean, I'm not surprised because that's what we also found that many of these systems have a lot deeper um, storage than previously considered. But then I would say, have you tried any mineral thermobarometers to contrast with the fluid inclusions?
Yeah, yeah. That's our next step.
Okay, cool.
Yeah, yeah,
I want to know what you get.
yeah, yeah.
That's
Thank you.
very exciting.
Mhm.
Okay, thank you very
Yeah, no,
much.
very good. Well done.
Yeah, and nice presentation. Thank you.
Thank you. No, it will be very interesting to know what you get for that setting, no? Really cool. Yeah,
Yeah,
look forward to
cool.
hearing.
Yeah, nice to talk to you.
Thank you.
Oh,
Likewise.
okay, thank you, and thank you, Henry, for the question. I think it's about 1 hour. It's great. Okay, do we have one more question? So, okay, Che Jiang has a question. She's a seismologist. Actually, she's at Münster in Germany now. She's working on the transition zone beneath Iceland. So she would like to ask you what insights about the interaction between mantle plumes and for
So that's a difficult
760.
question for a petrologist, I guess, because we don't have petrological evidence of that, other than geochemical evidence, I guess. But with the petrology, you don't have that deeper history is not recorded in the petrology. So
Mhm.
I guess the best way to go forward there is your geophysics, which is what you're doing. And potentially some combination with geochemistry. What do you think?
Okay, I think maybe she's typing right now. I don't know. Maybe Xiuquan Zhang, you can open your mic. Uh, actually, Xiuquan, I think it's in very early morning in Germany, I suppose.
Yes, thank
So
you
it's
for
fine.
connecting from Iceland. Yes, okay. But
Okay.
that's where that's nice that your physics comes in. I think it's really cool that we combine different lines of evidence.
Mhm,
So I'm a petrologist, so I love looking at the rocks and extracting all the information from the crystals, from the carrier liquids, and get to know everything about that I can from those. But then I love combining the information I have with inferences from geophysics and other methods. So I think that's really cool.
mhm.
Good luck.
Okay. Okay. It's a very good seminar. Let's conclude. Let's thank our speaker Dan for the talk
Thank
today.
you. Thanks for
Okay.
having me.
Okay, great.